Baumslag student, and we took many classes together. And he graduated at the same time as me in 2004, I think.
Yep.
And now he's an associate professor at Kingsborough Community College. And today he's going to speak about Nilpotent QX power groups.
Thank you. Delaram. Oh, there she is. Now I can start. I was waiting for Kathy. Yeah, so thanks, Delaram, for inviting me. It's a great pleasure to talk at the Alpha seminar. The work I'm going to talk about today on Nilpotent QX power groups basically comes from some work in my thesis together with some work I did later on. As Delaram mentioned, I did get my degree in 2004, so it's been 4 years, and I did come up with some other results since then. Of course, being it's an hour long, I can only say so much, so I'm not going to be proving anything, but instead I'm going to be throwing a bunch of results at you. Nevertheless, if you look in the paper that's published in Combinatorial Group Theory by Ben Fine, so on and so on, you'll see some of the work there with the proofs. And if it's not there, it's also in my thesis. And if it's still something that you don't want to look up, I'll be glad to send a PDF to you for at least $10. Anyway, my wife doesn't give me money. So anyway, what I want to begin with is telling you how nilpotent R power groups came to life. So I'm going to discuss how we led to what are called R completionists. And these results are pretty straightforward in a sense, if you already know some things about nilpotent groups. If you're not familiar with nilpotent groups at all, then the talk may be a little bit, strange, but, these things could be researched, I guess, and then made sense of. So for starters, suppose that we have a nilpotent group of class C, and let's say we have a subset of elements in the group G. Then there exist words which are known as Hall-Petresco words and abbreviated as Tor sub k of G bar, where G bar is the vector notation for G1 up to Gk. And it turns out that these words actually lie inside of the lower central subgroups, gamma sub k of G. And they satisfy this very beautiful relationship. Oh, speaking of beauty, good morning, guys. Sorry. They're both wearing red. And I'm wearing blue. So it satisfies this nice relationship where if you exponentiate each of the g's to some power k, where k is positive, then you get this product on the right, and you'll notice that the product on the right is in terms of the taus, and also you have these binomial exponents. Now, to get that equation is not trivial at all. In fact, it's a theorem of Philip Hall, and it requires a couple of pages. So it involves what is known as the collection process. And the main issue with this is not only does this equation hold, but also that the taus do lie inside of the lower central subgroups. That's important here. Now, it turns out after a lot of heavy-duty work that number 2 follows, namely if you have a finally generated torsion-free nilpotent group, then it has what's called a polyinfinite cyclic and central series. So in case you're new to this, let me remind you or say that a polyinfinite cyclic series is one in which you have factor groups which are cyclic. So if you take gi plus 1 mod gi, you get a cyclic group. And a central series means that every factor group is inside of the center of g mod gi, let's say. And also the cyclic groups that I mentioned are infinite cyclic, so they're isomorphic to Z. Now, it turns out that the length of any such series is actually invariant, so that means that if you try to refine such a series, the number of infinite cyclic factors doesn't change. And that invariant is what's known as the Harshx length. If you take, let's say, elements in gi plus 1 and you look at all of these cyclic factors, then it turns out that you can actually represent any group element as a unique expression u1 alpha 1 times dot 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 up to un alpha n. And again, the key thing here is that this is a unique expression, okay? Clearly, if there was torsion in the group, then the alphas can vary, okay? So in the language of Philip Hall and Maltsev, who are the ones that actually came up with some of these results, in fact, we say that this set of ui's is a Maltsev basis for G associated with this series. And alpha bar, which is the exponents in vector form, is what are known as the coordinates of G. Okay? By the way, if there's any questions during the talk, just ask. And if I don't know the answer, I'll just say it's obvious. You won't question me because you'll feel silly. I learned that from Dr. Baumslag. Okay. So let's suppose that we have G as before. We have the same Maltsev basis. Then it turns out that a heavy-duty theorem due to Hall and Maltsev says that if you take any two group elements expressed in terms of the Maltsev basis, when you multiply them together, you get again something with respect to the basis, and it turns out that these f functions are actually polynomials with rational coefficients. And similarly, if you exponentiate any group element in terms of the Maltsev basis, you again get something in the Maltsev basis where the GIs are also, bless you, polynomials and rational coefficients. And it turns out that to get this result is not trivial. In fact, it requires the use of the whole Tresco words and collection process. In fact, in Phil Paul's notes, it requires at least a page. And you know, if you've ever seen his work, you know that he leaves out some details. So for the ordinary guy, it's at least 4 pages. Okay. In fact, the proof of this will be replicated in an upcoming book called Nilpotent Groups, which is going to be a fantastic book. I know the authors personally. It's actually going to be written by Anthony, Marcos, and myself. So all of you are obligated to buy it.
We ordered
Anyway, you can pre-order now, but I don't take credit cards. Discount's very expensive. Okay, so now those are the preliminaries. Now it turns out that this information that I've given you so far can be used to talk about what is known as an R completion of a nilpotent group. So let me now inch in towards that. By definition, a binomial ring is an integral domain of characteristic 0 with unity such that whenever you take an element in the ring, then you can define these binomial coefficients. So each of these binomials R, K are actually unique elements in R. Okay, so some examples of such rings are Z, if you have any field of characteristic 0, and also if you take f of x, you know, f square bracket x, where f again is a field of characteristic 0. And of course, you can extend that to say you can have n variables, n indeterminate variables. So f square bracket x1 up to xk. All right? And of course, f square bracket x is going to be important for us because q is a field of characteristic 0. Okay, so here's the deal. Philip Hall had an idea, and it basically said, you take this, you take G to be a finitely generated torsion-free nilpotent group. You have a Maltsev basis for it. In fact, there are many different ones, but let's take one of them. And now let's take a binomial ring R. Then what you can do is you can actually form these, the set G exponent R to be the set of all these informal words. So think of these guys as just elements, and GR is the set of them. Now, it turns out, once we define a group operation on this, this will become known as an R completion of the group G. So prematurely I wrote that. Okay. Now, these functions f1 up to fn, g1 up to gn are the same polynomial functions I mentioned earlier. Remember, if you take two elements in terms of the Maltsev basis, when you multiply them, you get again something with the Maltsev basis, but the exponents are polynomial functions with rational coefficients. Using those same polynomial functions, you can say, hey, let me take those polynomials and now talk about that kind of operation on this set. Except now, of course, instead of putting integers into those polynomials, you're going to put elements of R into the polynomials. And the whole idea is that since these polynomials have rational coefficients, in fact, it turns out that they actually have binomial coefficients as well, binomial rings admit those types of elements. So everything works out nicely. And with these polynomial functions, as before, we can talk about these relationships 1 and 2. So we have the same idea as before, but now, as I said, the alphas, the betas, and lambda all lie in R. It turns out after sweating it out a little bit and using a result of field theory, one can show that G exponent R, or the completion of G, is actually a group, all right? And in fact, after sweating it out a little bit more, you can prove that it's a nilpotent group, and the class is actually the same as the class of G. Again, I say sweat it out because I sweated it out to actually learn these things. Again, this is all known material.
So G is torsion.
Are there any other questions?
Yes, it's no.
You have to excuse me. I just woke up. I was on the bus and I fell asleep. Okay, I'm sorry.
So G is embedded in its completion because G is torsion free, or?
Well, G is embedded in the completion because Z is embedded in R. R is a binomial, binomial ring. So clearly, take any ring, Z is kind of living in it because you can add elements. So it's actually embedded because of the fact that the ring embeds into R. Okay. All right. So as I said, G exponentiated by R, or the completion of G with respect to R, is a nilpotent group. Okay. By the way, this result was actually known, if my history serves me correctly, earlier. In fact, Maltsev, in an earlier work, showed the following theorem. He said that if you take a finitely generated torsion-free nilpotent group, it actually embeds into what's called a divisible nilpotent group. Divisible just means that every element in the group has a root, and any root, and it's unique. Okay? So in the sense of what we're talking about, it actually follows that any such group is Q isomorphic to G completed by Q. Okay? This was a well-known result, and it's termed as Maltsev's embedding theorem. Okay, so now it turns out that this idea that Maltsev had triggered a more axiomatic approach. Namely, let's actually define a nilpotent R-powered group in such a way that this G completed by R is one of these objects. So now I'm going to lay down a few of the axioms which hold. So let's suppose G is any nilpotent group, and let R be a binomial domain. And suppose that for every element in the group and alpha in R, we have this uniquely defined element which will be denoted G exponentiated alpha. I'll just say G to the alpha, okay, as we do in undergrad school. So this R action, which gives us G comma alpha to be G to the alpha, makes G into what's known as a nilpotent R group, or as I'll usually call it, an R power group, if the following axioms hold. And you'll notice number 3 in particular. First of all, number 1 are the usual things we want to happen. For example, G to the first power is G. Remember that the number 1 is actually the unity element in the ring, and every binomial ring has one. Furthermore, products and exponentiation work the way we would hope for. Number 2 says if you exponentiate a conjugate, then you can distribute the exponent in. And number 3 is our friend, which is the whole Petresco axiom, as it's called. So now we want this rule to work for our new type of group, okay? And we know that if we have alpha to be Z elements, it does work from the earlier result I mentioned to you. By the way, you'll notice that when I write these tors down, all of the binomial guys are actually up to alpha K. K is the nilpotency class of the group generated by those G's, okay? And when I say group generated, I'm talking about the smallest subgroup which contains those elements, the intersection of them. It turns out immediately from the axioms that you have these 3 results, which again are kind of things we want to happen, right? So you have an inverse of G to the mu is G to the minus mu, and so on and so on. All right, so R could be any binomial ring for this to hold. Why do I care about Q square bracket X, which I'm going to now call QX? Is that okay? Mm-hmm. Is that okay?
Yes.
Everybody has to say yes.
It's
I'll leave it, First of all, QX is a Euclidean ring, so it has a division algorithm. And once you have that, as you know, you have a PID and a UFD, so life is good. Furthermore, because it's a PID, it satisfies the ascending chain condition, which means it's a Noetherian ring. And that's a very good thing because it turns out that some of the results from module theory can carry over to these groups. As you know, well, maybe you don't know, but I'll tell you, not all binomial rings are Euclidean. Not all binomial rings are Noetherian. For example, let's say we take Q square bracket x1, x2, x3, so on and so on to infinity. That's certainly binomial, but it's not Noetherian. Okay, so here are some examples of such groups. Well, we started out with this one. If you take the QX completion of a Trojan-free finally generated nilpotent group, it certainly does make a nilpotent QX power group. Now, to get this, you actually have to verify those axioms, and again, you do that by sweating it out. In particular, number 3 does require a little bit of work because you have to show that that identity holds, but it turns out that since that identity holds for the integers, it's going to hold for R in general. And again, this goes back to a result of field theory. There's something that says that if you have a polynomial which works for infinitely many elements, then it's going to work for all elements. And since Z has infinitely many elements, it holds. Here's another example. It turns out that every QX module is an abelian QX group. Of course, you have to translate the module operations into these exponential laws that I'm talking about. For example, the one that you may think is a little weary is the fact that if you take, let's say, R times X plus Y equals Rx plus Ry, that one would translate to saying that xy to the R power is x to the R times y to the R. Well, it's not obvious that that holds because you have to see that, it really does work, but in fact it's true. Because, well, I don't know, should I say it or, well, you could read about it, okay? It comes from the Hall-Petrescu axiom. Because it turns out that all of the tors, except for one of them, vanish. All right? And I'm not going to say anymore, I'll let you play with that. And by the way, the converse is true as well. Not only is a QX module abelian, but if you give me an abelian QX group, it's a QX module in the obvious way. Now the next one is a little bit longer, but nonetheless it's a very important example. So let's say you take any associative ring, and it has unity, and let's say that it contains QX in its center, let rho be a nilpotent ideal whose exponent is n plus 1. And then it turns out that if you take this group G to be 1 plus A where A lies in rho, that's actually a subgroup of the group of units of R tilde. And it could be proven with a little bit of effort that that is actually a nilpotent group of class at most n, where n plus 1 is what kills the ideal. Okay? The way you prove that is by sweating it out. In fact, if you look in the book by Robinson, you'll see a nice little proof there. Again, a beautiful proof will show up in the upcoming nilpotent group. But anyway, it's called advertising. So, if I take any lambda in R tilde and take G in rho, then I can define this exponentiation, which is the usual binomial expansion. As we know, that holds in a ring. And notice that I stop at lambda n G to the n because G to the n plus 1 would get killed, since rho gets killed at n plus 1. It turns out, after verifying all the axioms, that the group G equipped with this axiom is a nilpotent QX power group. So if I restrict myself to just the QX elements alone, the lambdas that lie in QX, it works out to be nilpotent. Of course, QX has to lie in the center, otherwise you don't have commutativity. You want to have a commutative ring, By the way, it turns out that one such instance is when you have the group of units to be the upper unit triangular matrices over Q square bracket X. So if you take all matrices with 1 on the main diagonal, zeros beneath, and all QX elements above, that actually is one of these groups. And it's abbreviated as UTN-QX, not TN sub 1, as somebody's been writing in my beautiful book. Anyway. What I want to do now is just throw down some preliminary things at you. And this stuff is just going to set us up for the main results, all right? You got to prep for all these things. So first of all, From this point on, whenever I write G, it's going to represent a nilpotent QX power group, and K will be a binomial subring of QX. All right, so by definition, you have the notion of a K subgroup and a K normal subgroup in the obvious way. Namely, if you take a subgroup of G and it respects the exponentiation, then it's a K subgroup. Meaning that if G is in H, then G to the alpha, you want it to be in H as well. And of course, if H is normal, then you call it a normal K subgroup. So these are standard things. For example, after playing with the axioms for a couple of minutes, you could verify that the center of a group, Z parentheses G, actually is a normal QX power group of G. You can do that easily once you play around with property number 2. Because if you take H inverse GH to the alpha commutes in or distributes in. So that gives you that. Also, the intersection of an infinite collection or a finite collection of K subgroups is a K subgroup. I was looking on the bus on the way here and I said, wait, it doesn't have to be finite. It's stupid. You could have any collection, any family of K subgroups, and it works. All right, so it turns out, again, applying the axioms, in particular the whole Petresco axiom, that if you take a normal subgroup in G, then Gn equal Hn implies G to the beta n equals H to the beta n. Okay? And that requires a little bit of work. Of course, to be normal here is very important. Otherwise, this doesn't hold. Now, it turns out that because you have this relationship, this implication, one can define a QX action on a group's factor group. So if I have a nilpotent QX power group G, then the action on G automatically gives me an action on G mod n because of this thing. This gives me the well-defined action. So consequently, if n is normal, then you have an action on G mod n, and namely, it's if you take Gn to the mu, you can write it as G to the mu n. And that turns any factor group into a nilpotent QX power group. So basically, all the things that we have in categories and stuff is happening here. This is what we would like. There are, in general, in fact, what are known as exponential groups. And in an exponential group, some of these things may not hold. But in a QX, nilpotent QX power group, they do hold. If you want to learn more about exponential groups, you can come to my talk in November at the group theory seminar. So it's more fun stuff. Okay, so if I have a set of elements in a group G, then it turns out that if I take the intersection of all K subgroups containing all K subgroups containing S, and I form their intersection, what I get is the K subgroup which is generated or K generated by those elements. So this is the usual notion. Notice that here it's possible to have an infinite collection of H sub i's. So intersections of such things, as I pointed out, are really K subgroups again. And these X's inside of S are what are known as K generators. Okay? So we all know what that is, I'm assuming. You generate a subgroup. Now suppose that we have two subgroups, two K subgroups in G. Then we can form what is called the commutative K subgroup. And by definition, that subgroup is the K group generated by all commutators H1 with H2. By commutator, you know what I mean, right? Or should I say anything? You take H1 inverse, H2 inverse, times H1, H2. Okay? Commutators measure how far the elements are from being commuting elements. Now it turns out that recursively one can define a commutator subgroup which is going to have I things in it, let's say, H1 up to HI. And you do that by just looking at it step by step. So you do the first I minus one of them, and then you take HI after that. And it turns out that just the notion of commutator subgroups alone requires a bit of work and effort. Okay?
So,
Yeah. Question?
well, for somebody that doesn't know, this is normal closure of these commutators in K.
Well, it
mean,
turns
it's
out,
actually-
it turns out one can prove that this is a normal, these are normal closures, yeah. I know where you live. All right,
You have to learn to teach us.
by definition, listen, I'm off today. I shouldn't even have to be, I could have been home sleeping. If I didn't like Dalaram, I would have been in a Starbucks.
You
right
sound like a Baumslag student.
So, yeah, right.
Listen, don't
We are
insult me.
such free-spirited
In a
people.
star.
We create problems
That's
amongst
right.
mathematicians.
Okay. Okay, if you have a chain of subgroups ascending from G0 to Gn, then it's called a central QX series if the following conditions hold. Each GI is a normal subgroup in the QX sense in G, and also the factor groups GI plus 1 mod GI are QX subgroups of the center of G mod GI. You'll notice if you have experience with nilpotent groups that this is just a generalization of central series. Again, if you're not really familiar with nilpotent groups, a lot of this is going to be extremely fuzzy. And if you'd like to learn more, I'll be glad to supply you with notes. I can give you my email address. But yeah, if I give you some notes, you'll be obligated to purchase more notes, and so we'll talk later.
First sample is free always.
The first page. The first chapter's free, yeah. Okay, so a lemma on QX subgroups, product of QX subgroups says this. And again, this just translates over from the usual notion in group theory. If you have two subgroups, one normal and one not, then it turns out that their product is always a QX subgroup, and furthermore, H times N is going to be the group generated by H and N. Now, if both subgroups are normal, then it turns out that the product is also normal in G. So again, to prove this, you might think, oh, it's obvious, but it's not obvious, because in order to show that Hn is a subgroup, you have to remember that you got to check that if you give me an element, then when I exponentiate it, I get another guy in the set. And to do that exponentiation of a product, one needs the whole Petresco axiom. So you got to sweat it out and really understand how those whole Petresco words work. And you know, some of us did sweat it out and learn these things. If not, we just take it for granted and we say it's obvious. Okay, the definitions of homomorphisms carry over in the usual way. So if you have a QX homomorphism between two nilpotent QX power groups, it means that there's a homomorphism from one to the other in the usual sense. And also, if you take, let's say the homomorphism is called phi. If you take phi of G to the alpha, it's the same as phi of G to the alpha. So it respects the action of QX. And the other notions of morphisms work in the obvious way. Consequently, it turns out that the isomorphism theorems work in the usual way. Again, respecting the action. One can prove this. Now, there are a couple of remarks I'd like to make which deal with abelian QX groups in particular, and bear in mind that abelian QX groups are just QX modules. First of all, as one would hope for, every QX subgroup of a cyclic QX group is again a cyclic QX group. Translating to module language, that means that every QX submodule of a cyclic QX module is cyclic QX. By the way, that works because QX is a Euclidean ring. Because if you think back to the old days, a subgroup of a cyclic group is cyclic because you need to use the division algorithm. So without that, you're screwed. Oh, you're stuck. Okay. My mother may watch that. What'd you say? Another result that I was reading on the bus and said, "Oh crap! I let out a certain hypothesis here." Well, maybe I'll leave it for you as a exercise right now. Read number 2 and tell me where I screwed up.
Where I made a mistake.
Yeah, where did I make a mistake? I realized it on the way here. I left out something. Don't say it until I drink my coffee. Hold on. Okay, thank you.
Yep.
Yeah, it should say every QX subgroup of a finitely
Right.
QX generated abelian. I left that out by accident. The reason why that holds is because QX is Noetherian. Remember, in module language, this would say that every QX module of, every QX submodule of a QX module which is finitely generated is going to be again finitely generated. Okay, so I apologize for that typo. By the way, if it's obviously non-Noetherian, this doesn't hold. So QX again is a special guy. Direct products of nilpotent QX power groups work in the obvious way. Namely, if you give me a direct product, you can just define the action by doing it component-wise. Whether you're an unrestricted direct product or a restricted direct product, it's all good. And finally, well, not finally, but the last thing on this page states that if you take a finally QX generated abelian QX group, then it decomposes into a direct product of cyclic ones. Again, this is something that holds in module theory. Once you have that your module is a PID. This is the usual decomposition theorem over PIDs. Okay. All right, so having said all that, what I want to say is let the games begin. So I'll say it. Let the games begin. Who the hell wrote that? Okay. Anyway. So the first theorem that I'd like to mention, and this is not due to me, but this is actually something that appears in Hull's notes and also in the book by Warfield. If you want to read a nice book on nilpotent groups, Warfield is a good one. It's a lot of work because you have to fill in plenty of details. Hull's notes are also a lot of work. But anyway, like I said, I'll be glad to supply you with notes if you'd like. The theorem says that if you look at the subgroups of the lower and upper central series, those guys are actually QX subgroups. Again, it's not obvious. You have to actually do some work to check that. By the way, from this point on, if it does come up again, gamma I means the lower central subgroups, zeta I are the upper central ones. If you don't know what these things mean, I can supply you with notes. I'm trying to be nice
Until
here.
you drown.
Yeah. Let's recall that there is this notion of a simple commutator. So if you have G1 up to Gn in a commutator bracket like that, it means recursively you take the first n minus 1 elements and then do it with G. Again, remember that if you take 2 elements, a commutator means the usual thing, and now you can expand on that notion. By convention, if you take a commutator of a single element, it's just that element. Well, it turns out that if you look at the lower central subgroups, gamma, sub, and G, those guys are actually generated, or I'm sorry, it's the group which is generated by all simple commutators. Now, this result actually holds for any for any group. Am I saying that right? Yeah, it holds for any group. But now I'm saying that it's also holding for QX power groups. All right, and again, you actually have to do a little work to verify this because when you form this group, you're actually looking at exponents from your ring QX. So you got to verify these things. I remember when I was doing my thesis, I was insisting that I should put a little QX down there because that was my notation earlier. But Baumslag said, you don't need QX because it's already embedded into the thing. So after thinking about it, I said, oh yeah, he's right again. That's, anyway, it turns out that from a result known as the 3 subgroup lemma, which I'm not going to get into, you can prove that if you take a commutator, QX commutator, of, let's say, 2 subgroups of the lower central series, gamma I and gamma J, their commutator lies in gamma I plus J. So if you take 2 of those subgroups in the lower central series and you form their commutator QX subgroup, you end up with a term which is a lot further down the chain. Okay? Now, again, and you know, we take it as obvious, but it's not obvious. The next theorem holds. It turns out that for every integer I, there's a QX module epimorphism from the tensor product of I abelianizations of G into this factor group gamma I mod gamma I plus 1. Now, the way you actually prove that is by first seeing that this epimorphism makes sense, and you actually have to check that this thing really does what it says. In other words, you have to verify that when you take such a tensor product, it does give you that. And the way you do that is simply, well, I shouldn't say simply, but the way you do that is by examining the whole Petresco words and checking that, for example, if you take, let's say, ci raised to a power, then the power does go in as we said it should earlier. And to do that requires some work. By the
I
way,
didn't see definition of tensor product in group theory context.
Yeah, you see
Huh?
that-
What ring are you using for the
Yeah, rings.
tensor?
no, these are over QX. This is,
Over
I'm-
QX.
Yeah.
I'm looking at a QX module now.
Okay.
Because, remember, when you take an abelianization, you're looking at G mod gamma 2G. And that's abelian and it's QX group, so it's a QX module. So right now, these are purely these are QX modules.
But you can define tensors of abelian groups if you regard them as Z modules.
Mm-hmm. Yeah, so this carries
So in this
on.
case, it's not these are not Z modules.
I see.
Yeah. Well, these are QX modules, and that's why there's a QX
What
module
QX is
morphism.
that?
Again, you know, like I said, to prove this, you have to actually do it in stages. In fact, there's an earlier result, which I omitted from this, which says that, I don't know, maybe I could write, no, I won't write. There's an earlier result which leads to this, so it doesn't just come obviously. You know, I'm just giving you the main gist of it. But the beauty behind this result is that it pretty much it tells us, hey, if you know something, no, I don't want to write it, I'm going to get dirty. I'm on film here. It actually tells us that if we know things about the abelianization of the group, we can then extend it to the group itself. Because once you know things about these factor groups, it turns out that you can then go up the lower central series and say what happens in the group itself. Okay?
Hey, Steve.
Yeah.
That gamma, just notation, the theorem in the middle of that page.
Yeah.
The group on the right is QX
That's-
generated by the commuters, but what about the group on the, I mean, is that the regular
Well, that's
gamma?
the thing.
I mean,
That's what drove me insane. I remember being in city college at Gilbert's board. I'm like, why? But yeah, so gamma n
is the,
we know is a QX subgroup.
I see. So
And
you
this
don't,
thing
you don't
o-
need to say anything else.
No, this thing over here, this group, you would say, okay, that's just a group whose exponents lie in Z. But nevertheless, these guys actually come from a QX group, so they have exponents in QX. And if you multiply a Z with a QX, you again lie in QX. So in a way, I can visualize this as a QX subgroup as well. It's kind of a funny thing, but that's how it works. Here's an exercise. Take n equals 2 and try something, and you'll see. Okay, so the reason I mention this theorem at the bottom again is because, first of all, it's a beautiful thing. It tells us that the abelianization has some effect on the whole group itself. And for example, you know, it does lead to other nice results, which are very crucial. For example, there's a corollary which says that if you have finally a QX generated group with this set of generators S, then if you look at each of the factor groups, they're finitely generated as QX modules. And you also know what the generating set is, or what a generating set is. Namely, it's the set of all of these commutators where each of the S's vary over S, and it's modulo gamma n plus 1. So if you look at one of these factor groups, you now know what a set of generators would be. Okay? And this comes from the previous result because remember that mapping was a QX epimorphism. So the gamma, the factor groups, every one of them can be represented as one of these commutators. Okay, now the next result was actually first stated in, I believe, the work of Kargopolov and others. So it's a Russian paper. So there was about 5 authors, 4 of whose names I couldn't pronounce. And they actually they wrote a paper on what are known as sigma power groups, which turned out to be the same things that I was looking at, and I didn't know until later on. In fact, they actually proved something regarding the conjugacy problem, which I had done as well, but under a different context. So being, you know, if you prove the same thing in a different way, it's still good. You know, make sure you learn that. Okay, so it turns out that every QX subgroup of a finally generated nilpotent guy is finally generated. Now, You may recall that earlier I said a similar thing where nilpotent was replaced with abelian, right? And since it works for abelian, it'll work for nilpotent by doing some inductive procedure or whatnot. You know, you do an induction on the class. By the way, this actually holds even if the ring is Noetherian in general. You don't have to be a QX, you could be Noetherian. Okay? That was something I said earlier when I talked about the abelian result. Okay, the next definition I want to mention might be familiar to many of us in a more general sense. Let P be a property of groups, then if you have a QX series, meaning that each of these subgroups in the series is a QX subgroup, you call that a polyqx P series if, well, if each subgroup is normal in its following subgroup, and also the quotient, gi plus 1 mod gi, is a PQX group. Okay, so P is going to be a property, and the property that we're going to care about is shown in the next result. And this result was actually shown in Warfield's book on nilpotent groups. He proved that for any R, any binomial ring R, it says that if you have a finally generated group G, then it's going to have a polyqx cyclic and central QX series, and conversely. Again, if you drop the QX stuff, you'll notice that this is very similar to the usual ideas, you know, to the usual result on nilpotent groups. And again, to prove this, well, if you prove this for QX, it's not so bad because of the fact that QX groups are PIDs and Noetherian. But in general, you know, you got to count, you know, you got to take it a different way. And of course, if you read over Warfield's book, he just says, oh, it easily follows from corollary so-and-so. But then when you look at corollary so-and-so, you're like, how does it easily follow? You know, but that's the way it is. Now, similar to before, we have a notion of a harshx QX length. And the harshx QX length will be the minimal length of any of these such series. So if you give me a finally generated group G, in the QX sense it's generated, then if I look at all of these types of series, and I take the smallest length possible of all of those, that's the harshx QX length. So as you know, when doing things with nilpotent groups, you always want to do things, or most of the time you want to do things by induction. You either do it by induction on the class, or you do it by induction on the harshx length. So now we have a notion of a harshx length. Okay? Another one which is pretty cool says that if you have a nilpotent group, you know, of course QX, and the class is 2 or more, then if you take any element and you look at the subgroup generated by that element and gamma 2G, remember gamma 2G is just a derived subgroup in the QX sense. It's G bracket GG. It turns out that that subgroup H is also clearly nilpotent, but it's of class less than C. So now this also leads to some induction properties that we can use. Okay. All right, so now that all of that is in the way, oh yeah, and by the way, this works when you have QX, but I think that if you just look at any, how does it go? Any Euclidean ring, it'll also work. Because one of the proofs that I know of this theorem in the general sense is that you have to use a subgroup of a cyclic group as cyclic. And remember earlier I said that in order for that to hold, you have to have a Euclidean algorithm. Division algorithm. What am I trying to say? Yeah,
Yeah.
I said it right.
That's good. We call it Euclidean.
I call it whatever I want, it's my talk. Okay, yeah, right. Some basic definitions now on torsion sets are as follows. If you take an element G, you call it a torsion element if there's a non-zero element in your ring such that G to the alpha is 1. So this is the usual notion, except that now your exponent comes from the ring. The set of all torsion elements will be called tau of G, not to be confused with the whole Petresco words where there's a subscript. And also, you say that a group is a torsion QX group if every element satisfies the torsion property above. Finally, you say that G is a torsion-free group if G to the alpha equal 1 implies either G is 1 or alpha 0. These are the usual definitions in group theory, except now we're extending to the ring QX. Now, a theorem that shows up in Hall and in Warfield says that if you look at the set of torsion elements, it actually is a QX subgroup and it's normal in G. And also, if you look at the factor group, it's torsion-free, so that's obvious. Furthermore, if you have that G is torsion-free and you take any two elements satisfying the equation G to the alpha equal H to the alpha for some non-zero alpha, then G must equal H. Okay? Again, to prove that requires a little bit of work. All right, so now we'll move on to another notion. We have these Dehn problems, if you know who Dehn, right? Dehn. Dehn's problems deal with some things like, okay, if I give you a Anthony, why don't you say, let me have my coffee. Anthony's going to talk for me.
Well, so in my talk, I guess I'll say the same thing, but Max Dehn had three problems in 1911, actually. He came up with three main problems that really drive the research in combinatorial group theory. They are the word problem, the conjugacy problem, and the isomorphism problem. So the word problem is given a finally presented group, and you take an element in the group, which is, can you tell whether or not that element is the identity? That's the word problem. And the conjugacy problem is given, again, a finally presented group. You take two elements, can you tell whether or not they are conjugate, that there's some element that conjugate that element to give you that other particular element U and V. And the isomorphism problem, they were given two finite presentation. Can you tell whether or not these groups are isomorphic? So this really kind of drives the research in that field. But however, all these are algorithmically undecidable. That is, it's not general that these things are solved, but for specific groups, you can solve the word problem, the conjugacy problem, and the isomorphism problem.
Thank you, Anthony.
That's beautiful, actually.
So in the next 2 weeks, I'll talk about the isomorphism problem of a particular one related group.
Actually, we might talk,
that
we'll
was
have to
commercial.
define the same stuff. So, you know, thank
By
you
the
so
way,
much.
we didn't even rehearse that. That was
amazing.
I want to see if he's ready, that's all. Okay.
Oh, no,
All right, so now, all right, so now, eyes on me now, forget Anthony. Well, look at me now. Okay, good. So, coming back, so it turns out that if you have a finitely QX generated nilpotent group, you have a solvable word problem, generalized word problem, and conjugacy problem. Generalized word problem, remember, means that there's an algorithm which decides whether or not a given element is in a subgroup of the group if you have a presentation for that subgroup. As I kind of mentioned earlier, the conjugacy problem, as well as the other two, were solved by Kargapolov and others for finally generated nilpotent groups, but the ring that they had talked about is actually a special ring which satisfies a collection of equations over modules, or module equations. But it turns out that QX satisfies them. I didn't notice until after I finished my thesis, and
Fortunately.
yeah, but I actually found out that my methods of solving these were different from theirs. Okay, so
Can I ask a question? What about the linearity of these groups?
I don't
has it
know.
been addressed?
I don't look at linearity of things.
Right,
so
and you
I
know
don't
whether they could be embedded in some, in some.
They can
group.
certainly be embedded, probably.
Because, you know, I don't know, we use the result in our paper where, you know, we talk about the F completion, ZX completion.
That's right.
These fully residue free groups are all embeddable
Yes.
into a Lie group that
I'm
is
sure. Yeah.
connected and semi-simple.
I'm
you know.
sure these can be embedded into those types of things. I haven't looked at it yet.
Right.
Yes.
So, the non-abelian ones, yes, go ahead.
Well, we know that these problems are solvable for finitely generated nilpotent groups
That's
as
right.
well. So I was wondering how similar.
The proofs are.
Yeah, I mean, how could you have to?
Well, the word problem works pretty much the same way, because to solve the word problem, you use the fact that if you take an element in your group, you can represent it in terms of some polycyclic series. And then once you have that, you know that you can just see if the word equals 1 or not by looking at what the exponents are and what the relations are. Now, the conjugacy problem is solved in a different way here than it was done by Blackburn, whose proof is also in Gilbert's book, which is much simpler. The proof uses a piece of that, but not all of it. I had to do some other things to get that proof for the conjugacy problem.
Can we also generalize QX nilpotent group to QX polycyclic group or something similar?
Like solvable or whatnot?
Polycyclic
Yeah,
group.
you could lay down axioms and define such a group and then find similar results, yeah. You know, again, the whole reason that this was done was because of the fact that Hall noticed that there were these completions, which Maltsev knew earlier because of the divisible nilpotent groups. But certainly you can axiomatize? Whatever. You could do that, and I'm from Brooklyn, I can't say that. You could do that for other groups as well. And in fact, I've thought of those things, and it's certainly worth checking out. In particular, maybe talk about metabelian QX power groups. So yeah, there's other things you can do here.
So does a fully residual nilpotent group embed into the completion? I mean, that's an analogous result to the result of Alexei Nyasnikov and Remeslenikov.
Right.
They proved that if you have a fully residually free group, that it embeds into the.
Well, they have
Centralizer extended.
they have
Right.
centralizer extensions, and you remember there's an axiom they use which says if two elements commute, then when you multiply them and raise to a power, the power distributes.
Right. You don't-
Remember that happens here in the case when you have class 1, so I'm sure that...
So you probably are doing, in some sense, you're actually at the footsteps of algebraic geometry of,
Oh yeah, I know I am.
over nilpotent groups.
I know
Yes.
I am.
Yeah,
It's
so
just
you
a matter
basically
of
have to
pursuing.
speak about,
Yeah, well, that's why I made
That's-
friends with you, I need you.
well, I am
No,
stuck.
these things are certainly out there, and we're going to explore them.
Right, that would be very,
Absolutely.
yeah.
Absolutely. There's more to come. I haven't been doing
Maybe
these
they'll
things.
give you the Fields medal that they did not give to,
Well,
to,
Let's
Olga
not get
Kalankovich
overambitious.
and Alexei
no,
Nyasnikov.
let's. No, I haven't thought about these things in about...
How old are you? I'm sorry, I didn't mean to be personal.
I can disappoint now.
Oh, yeah, isn't it?
How old am I?
I didn't mean to be
How old do you
personal.
think I am?
I don't discuss age in public.
Do I look over 40?
Answer.
Precisely for that reason, I'm too old.
29, I like that.
Just say under 40. That's,
I'm under 40.
that's
I got time.
So
That's it.
get
No,
started.
you know, in all honesty, I haven't thought about these things since my thesis because, as some of you know, I was busy writing some books. So my energy went to that. But now I'm getting back into the more interesting math, I guess.
Plus, you've probably been teaching 5 or 6 courses
And I'm
per
teaching
semester.
a lot, and yeah.
Yes.
So anyway, all right, so look,
So come on.
earlier I said something which nobody questioned, which is the following. When I have a group and I take its Q completion or QX completion or R completion, it turns out that completion depends upon the Maltsev basis that one chooses, right? I mean, imagine I have a finally generated torsion-free nilpotent group. I have a Maltsev basis U1 up to UN, and then I take those exponents and say, hey, let those guys live in R rather than in Z. But what if I were to choose a different Maltsev basis for G? Now, all of a sudden, the Maltsev basis is different, so the expression for that same group element will be different. Does it matter which Maltsev basis I choose to say the R completion? Well, it turns out this theorem says no. If you have a group which is finally generated torsion-free nilpotent and you choose 2 different Maltsev bases, then when you complete those with respect to the bases, it turns out that they're QX isomorphic. And it turns out that this result comes from a theorem in my paper, and the theorem that I proved uses the collection process that Philip Hall used in his work. And in fact, you know, in Philip Hall's notes, he says something similar but doesn't bother to prove it. When I started writing down the proof in my thesis, it took about 5 pages. So it was a lot of work. But nevertheless, this is obviously an important result. You know, you don't want to worry about which Maltsev basis you choose when you want to complete something. Okay?
It's torsion free.
Yeah. So, you know.
If it wasn't, then you'll be in problems.
Yes,
You
yes.
decide.
Yeah. Now, the next few things I'm going to discuss with you are my things, meaning that this doesn't appear elsewhere. So we have what are known as finite type and pi-primary QX groups. A group G is a finite type if it is a finally generated torsion QX group. So notice that this is somewhat of an analog of being a finite group, okay? Because in a group, if you have every element as torsion, it doesn't mean it's a finite group. If it's finitely generated, then there's some hopes of being finite in a sense, so this is like an analog. And it turns out, one of the things I showed is that if you take a normal subgroup and you look at the factor group, if both of those are a finite type, then G is a finite type. Now that in itself is not a difficult thing to prove at all, but the next theorem is pretty cool because it says, hey, if you have a finitely generated Nilpotent QX group, then the center is a finite type if and only if G is a finite type. So as you know, in Nilpotent group theory, knowing something about the center can give you some information about the group itself. So this is something along those lines. Okay?
These are your results.
This is my result, yeah.
And definition too. You just
This is
read
the-
the definition.
Yeah, everything from this point on is mine. Yeah. Now, the next thing I'm going to mention is the notion of a pi primary component, which you may already it sounds familiar when one talks about abelian groups, right? So let pi be a prime in QX, then the pi primary component is the set called G sub pi, which is all elements that when you raise them to a power of pi, you get 1, where that k value is a positive integer. Notice that this is kind of like a p, what is it called, a p element or something?
P-etic.
No, when you take an element and raise it to a power of p, you get 1. It's like a p element of some type. So this is an analog of that.
Well, these definitions work for our groups.
Yeah, this will work for R in general, sure. Now, along the same lines, G is termed a pi primary group if every element in that group is a torsion element to some power p, of pi, I mean. And if G is finally QX generated in pi primary, we say it's a finite pi type. Okay? So my thought along these lines was, hey, we have this notion of a finite p group, now we'll have a finite pi group. Okay? As you know, finite p groups are what? Well, they're kind of special because they're nilpotent. And not only that, there's some residual properties one knows about things. So anyway, we'll lead to that. It turns out, after sweating it out, one can prove that if pi is any prime, then G sub pi is actually a normal subgroup of G. Now this is not obvious at all, because let's think about it. If you take two elements, which have the property that when you raise them to a power of pi, you get 1, how do we know the product of the two elements does the same thing? Well, clearly if it's abelian, it's easy. But if it's not, now you got to sweat it out. But it's true, it does it. Okay? Turns out, and maybe you could tell me where this reminds you of something. Turns out that if you have a group of finite type, then it's a direct product of these G sub pi i's, where pi I ranges over all primes in QX. Does this look familiar? If not, I'll bring you down to earth with it. If you have a finite nilpotent group, it's a direct product of its silo p groups, p subgroups. This is the analog. Again, this heavily relies on the fact that QX is a UFD. So notice I hit everybody, right? We had a PID, a UFD. So everybody was important here, and that's why QX is cool. QX is even more cooler for the whatever. For the next, it's a Brooklyn thing. Okay. So this is the analog, which I thought was very nice. Now I want to state for you two residual properties. If you have a finitely QX generated nilpotent blah blah blah, G is a finite dimensional over. We say that it's finite dimensional over Q if it has a polyqx cyclic and central series, which we know it does, right, from an earlier result. But it satisfies the property that if you look at the factor QX groups, and if you view those as vector spaces over Q, because remember, each of those quotients are cyclic, and they're modules, so they're cyclic QX modules, and you could think of those as being vector spaces whose coefficients or scalars lie in Q. We want those guys to be a finite dimension as vector spaces. Well, it turns out that if you look at a finitely QX generated nilpotent group, it is residually one of those things. So I'll let you soak that in. Take your time. I only have one page left.
You're already running over time though.
I have 10 minutes. That's wrong. So you don't believe me?
You have one.
Uh-uh.
You have
Started
one.
early.
Your watch might be
You have
wrong.
one more.
Maybe you started early.
My watch is
Because we
wrong?
came in when it was.
Oh man, I'm sorry.
10:30.
That's why you wanted to start, and I was like, no, let's wait.
You have a
Oh, I'm
minute.
sorry. No, look, I'll take as much time as I want. I'm an associate professor. I'm sorry,
You
okay.
want the whole world to know this stuff?
Oh, yeah, right. Anyway. Hi, Mom. Hi, Mom. Okay. So anyway, that
I'll
result
edit
is,
it.
I only have a couple more things left. I could actually kill it in 1 minute. The next theorem is very nice, and it actually uses the previous one that I had mentioned. If you have a finitely QX generated group and you have two elements which are not conjugate, then there is a nilpotent QX group called B of finite Harshx length, which is finite dimensional over Q in the sense I just mentioned, and has the property that if you take it has the property that there's a homomorphism from G into B, such that the images of those non-conjugate elements remain non-conjugate. So recall this is the notion of conjugacy separable. So it turns out that we have now this notion with these finite dimensional over Q guys. So this was not in my thesis because at that time I couldn't prove it. Now it's actually a work in that earlier slide I showed you, and the proof is about 1.5 pages.
This
It's not true.
homomorphism doesn't have to be an epimorphism.
No,
Okay.
homomorphism.
Mhm.
Yeah, to build that B, well, it turns out the proof is on the Harshx length. If the Harshx length is 1, then it turns out you're looking at G as a cyclic. And if G is cyclic, then this non-conjugacy relationship boils down to the previous theorem, because you're looking at something that doesn't equal 1. And if something doesn't equal 1, then you could map it to another thing not equal to 1, because it's residually a finite dimensional over Q. And then when you do that, you're looking at a non-conjugacy thing in its image again. Now, if you do induction on the Harshx length, a lot of stuff happens. And believe it or not, the proof uses some of the things proved in the conjugacy problem. So it's pretty cool. Here's another result which is not in my thesis. I came up with it later. Let G be a finitely QX generated, torsion free. For every prime P, G is residually a finite pi type. So this reminds us of a result of Grunberg. Yeah, exactly. By the way, this notion requires what is known as a pi radicable Nilpotent QX group. And once you define that, there are some results you have to prove which lead to this theorem. I didn't state all of them because I worried I would run out of time. Anyway, last but not least, if you know about Hopfian groups, it turns out that every finitely QX generated guy is Hopfian in the QX sense. Now, bear in mind, I didn't discuss everything I would have discussed if I had more time, but I hope that you got the gist of it. And let me mention that there's a lot more things that can be done with these groups. So if you want to ask anything of me, or maybe you're interested in some of the things I said and you want to do something with it, let me know. All right, I'm going to go to Gilbert's class now, since I blew him off for the last 2 weeks. Thank you. Thanks.
Are there any questions or?
Where did you buy your coffee?
If there are any questions, the answers are all clear. I told you that earlier. No, if you have any questions, feel free to email me once more. I'm sorry, let me just, if you're interested. As a teacher, it's my job to want to help. So there's my email address there.
So let's thank Steve again.